All right, for another example, we have this. So for the first one, we have to define everything here. So we have a composite wall, but this is quite a different setup, right? So you have a 3 by 5 meter wide wall with a cross section of 16 centimeter by 22 centimeter. Okay, but that's only the brick, no? That is only the brick. And then you have a plaster layer, a foam layer, okay, and then you have the given coefficients for that, thermal coefficients. The indoor and outer temperatures are given. The convective heat transfer coefficients are also given. And you want to find the one-dimensional heat transfer, or the heat transfer rate, no, to the wall. So based on this, no, the indoor is 20 degrees Celsius, the outer is -10. So based on this, the inner side is the foam. So the inner side here is this. So you have 20 degrees Celsius here, and you have 20 degrees Celsius here, you have 10 degrees Celsius, oh, sorry, -10 degrees Celsius outside. So what can we do here? No? Is we can find the effective resistance of this wall. No? And then after that, we can find the heat transfer rate to the wall. But to make things simpler, because this is a different cross section, no, or this setup, no, we can just, sorry, this is a repeating section of the wall, meaning you have multiple layers of bricks here, up of this section and then lower of this section. Then what we can do is that we can only compute for this section, and let's define that this is just, we can just define one section of this wall, which is just, let's say, for example, just 1 meter by, if this is 25 centimeter, this is 25 centimeter. So we will define only the heat through this section of this wall, and just we can multiply this later by this one, no? So we will find the heat flux through this wall, or sorry, we will find the heat flow rate through this wall, and then we will find heat flux, no? We will convert this into heat flux, and then after that, we will find the actual Q for the whole wall, no? Because again, in a wall, you have multiple bricks, right? So, solving for this, or understanding this, we want to represent this wall in terms of its thermal conduct, also thermal resistance, no? So if this is 20 degrees Celsius, then you have a resistance here that is the convection, no? Heat transfer, which is 1 over, I'll just write here HI, and then the area, no? And then after that, you have a foam layer. So the foam here is, I'll just use 1, no? So we have L over Ka. So 1 here is the foam layer. And then you have another layer here, which is the plaster. Okay? So this one is the plaster, no? I think I'll just represent this. Yeah. Okay. So for another thermal resistance layer, so you have L over Ka 2, no? And then for this layer, so as you can see, you have a parallel layer here. You have a layer of plaster, brick plaster, no? So as we can see here, we can treat this as a parallel circuit. No? You have 3 here connecting this node. Yeah, I'm sorry, but this will not be that amazing to look at. Yeah. Okay. Okay. So you have here plaster, you have a brick, you have another plaster. So everything here will have an L over Ka, no? I'll just write down later. And then for this one, we have a plaster layer again. So this is the plaster layer again. And you have another L over Ka. So I'll just write this down as 1. Sorry, this would be 3, 4, and 5. Okay. And then this one for the plaster layer, we have 6. And then the convection, it transferred for this last node is 1 over HO A. No? And then this will be -10 degrees. So the heat transfer is going from the left the right, no? Just remember that as well. Yeah. Okay. Okay, now how do we do this? How do we start this off? So the thing about resistances, you have to start with the parallels, no? So when adding resistances, it is fairly easy, you know, if you have resistance or you have series resistances, you just add the resistance. So basically, you just let's say R1 plus R2, okay, for the effective resistance. But for parallel, take note of this. For parallel, to solve for its sum or effective resistance, the 1 over REFF is equal to the sum of the resistances, no? The R1 here, no? So we have R1 and then plus R2 and so on, no? Okay? Yes. Where is my note? Yeah. Back. Just try to figure this one. No, 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 no. Not like this. No. Sorry. I think I need something wrong. So 1 over R1 plus 1 over R2. Ayan, sorry. Okay. To find the parallel sum, no? So we can do this. No? And you can find the effective resistance of this one. Okay. So we have 1 over REFF of 345. That is equal to 1 over R1. So R1 natin dito is KA over L ng 3 plus KA over L. Kasi, sorry guys, no, but this is reciprocal. So we have to find the reciprocal of L over KA. So this should be KA over L. And then plus KA over L of 5. Okay, now you can actually rewrite this in a different way now if you want. But anyways, so we have 1 over REFF on 345. And we can solve for this. So the K of the 3-knot plaster is, we have 0.22. So 0.22. Just take note of the units. I will not write the units anymore. And then the area here. So the area here, we are defining only for this certain section here. So you have here 25 centimeter by 1 meter for the area. But in this case, since the layer of the plaster here is just 1.5 in height, no? So this is 1.5 in height. So we just multiply here 0.015 centimeter, which is in meter, in meter, and then 1 meter. No? So 1 meter in this, in 3 dimensions, no? In width. No? And then over L, so L here, the length here of plaster is from here to here. So this will be 16 centimeter or 0.016 meter. Okay. And I do this again for the brick. So for the brick, you have 0.72 thermal conductivity. And then the height of the brick is 0.22 meters or 22 centimeters. And then by 1 meter only. And then the length is also 0.016. Okay, so one technique here is actually since this is equal, no, this 3 and 5 is equal, as you can see here. These sections are both equal. I can just multiply this by 2 if that's okay. I'll just multiply this by 2. Since we can just add a duplicate of this basically. Oh. So if you solve for this, you can find the effective resistance of 345 using your calculator. I'll just show you how to do this. So we have, if you want, you can just directly shift solve. We have the luxury for most calculators times 0.22. 0.22 times 0.15015, then 1, okay, 0.016 plus 0.72 times 0.22 times 1. So I'll just remove the 1, that's 0.016. Oh shit, so x here is 0.097. Sorry. we have a wrong units pala dito, no? So this should be only 0.16 in centimeter nga pala ito, no? So this should be so so you have 0.97, so 0.9697 Kelvin per watt. Okay. So what we can do here after that, so since we have defined this, we can just add this for each, no? We just solve this to find the total. So also for this, and also for this to find the total. So I'll just find the total resistance directly using the calculator, no? But just to make things a bit quicker. So you have 1 over, let's see, this is what should store A. So you have 1 over HI. So HI here, um, where's HI? So 10, and then the area air. So the height of this layer here is 25 centimeter. So 0.25, 0.25 times 1 meter plus you have L over KA. So for the foam, you have this is 3, no? 3.03 meter. And then over KA, so the foam is 0.026 times area 0.25 as well, since that is the height times 1 plus the length of this plaster 0.02. This one is the plaster. And then over KA, so 0.0 or 0.22 times 0.25 as well times 1. Since we have two plasters, you can multiply this by 2. No. So this is the first plaster and this is the second plaster. I'll just multiply this by 2, guys. Sorry. Plus what? No. So this effective resistance of this parallel layer. So you have, I say this as A or 0.9697. And then the convective uh, thermal resistance, no? So 1 over HOE. So 1 over HOE, so 1 over 25 times 0.25, no? So the height is also 25 centimeters. You have 6.87 as your total thermal resistance, no? Kelvin per watt. So again, this is to take note, no? This is based on 0.25 meter by 1 meter cross section only, no? So take note of that because we will utilize this later. So if you solve for this, no, to solve for Q, you have the temperature difference, right? So E inside, so infinity because that is the air, and then the outside, the air, and then you have our total. So to solve for this, you have 20 minus negative 10. So that will be 30 over 6.87. So if you solve for this, the answer should be, um, so this will be 30 over 6.87. That will be 4.37. Okay, watts, no? So, but the answer is not this one, no? So why is that? So because this is again based, no? Based on 0.25 meter by 1 meter cross section only. That is why. So you have to consider the heat flux first, no? So you have to divide this by, to find the heat flux, you just have to divide this by this cross section because you have this. So we have 4.37 watts over 0.25 meter by 1 meter, no, to find the heat flux. After finding the heat flux, you can find the actual, no? So actual total per per the 3 by 15, no? Okay, let's solve this first. We have 4.7 over 0.25 times 1 or 0.25. So we have 17.48 watts per square meter is the actual value, no? So to solve for this, we can just multiply this heat flux by the actual area, no, which is this 3 meter by 5 meter wide because we have 3 meter, so 3 meter high pala, no? 3 meter high, yung actual height niya is 3 meter, and then you have 5 meter wide. So 5 meter, 3 meter. So the final answer should be multiplied by 15. No? So times 15, 3 times 5, or 15. That will be 262. 262.2 watts. Okay, so this will be your final answer. Okay, so that's it.